So I also have to apologize with those who already know some dynamics, because I decided to start from the very beginning, like easy definitions. And so the idea is that we're going, hopefully, to go towards higher dimensional, discrete holomorphic dynamics. That's the goal. But, well, you cannot go so high if you don't know what's coming in the first place, okay? So I also have to thank Sergey, because he gave you some definitions. So Sergey was doing, well, what I usually call, and people call, continuous dynamics. So he had a vector field and he had a flow. And so continuous comes from the fact that you're counting trajectories at real times, okay? So in this course, we will be doing discrete dynamics. So discrete dynamics by the way, can you see? Is it readable? Okay? And oh yeah, and I always forget to say it, but let me say it and I will repeat it several times. Thank you. I will repeat it several times. No question is stupid, so please ask as many questions as you would like to, okay? So actually, when I am thinking about discrete dynamics, what I have in mind is I have a map from a set to itself, okay? Easy peasy. And I want, so since the map is going from this set to the same set, I want to iterate. So I'm going to assume that it is globally defined, okay? So for every point in X, I get a point in X, and then, well, I can continue to iterate this map. And so what I'm interested in is, so this gives a discrete dynamical system because I can consider the composition of F with itself, say k times, and I'm going to call this, so in books and maybe in lecture notes when I write them, I usually put a circle in here to remind people that I'm going to iterate. It's not a power. But at the blackboard, well, I'm doing it here, so I will not put a circle because it's like an okay, it's weird, and it's not nice to see, okay? So this is the iteration of Fk times, and what we are interested in is we want to understand, so the goal, is to understand the long time behavior. What do I mean by this? What I mean is that I take a point, X in capital X. You want to understand, so you take the sequence of iterates, so this is the orbit, and you want to understand, so you want to understand the asymptotical behavior of this sequence. And as we were saying, so actually what one can do is, I'm going to call this xk, and you would like to know, does xk have a limit for k tending to infinity, for example? All right, so this is a reasonable question. And of course, you can say, well, this doesn't need to be the case, okay? So you can ask, as Sergey was doing, I can study all possible limits, okay? Of course, for the moment, I'm not giving you any structure on the set, but if I want to speak about limits, I need to have at least some structure on F and on X. So I will put a structure on X, and since this is holomorphic dynamics, for me, X will be a complex manifold. Don't worry if you never talk too much about complex manifolds. For us, in here, the complex manifold will be C or Cn when we go to higher dimension, the Riemann sphere, the complex projective space, CP1 or C hat, well, you can denote it as you want, or CPN. And that will be it, no more than this, okay? But so in here, X is going to be, so I'm going to add in here holomorphic. And in here, X is a complex manifold. And F is holomorphic. And I will get back to here in a minute. So I need to have some notation in here. So the forward orbit, I'm sorry, I cannot go very high because, well, as you see, I have a restriction. I'll try to go as high as I can. I forgot my high heels. So, okay, so given X in capital X, the forward orbit of X under F, well, I will denote it by O plus of X is simply... Ah, okay. Ah, okay. 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 Is it okay? Better? Okay. So, yes. So what's well? This is simply this xk for k positive, and then the backward orbit of X under F. Well, I will denote it by O minus of X. And this is simply the union, as I will keep k in here, as k is positive, of F minus k, I'm sorry, of the singleton X. Okay, I never said that half has to be invertible, so I'm taking the pre-images. Okay, I have sets. So could be that, so think about x squared. If you have x squared, so when you take the pre-image of 1, you're going to get 2 points, plus and minus 1, and so on and so forth when you go back. Okay? And
some cat would be empty also, right?
yes. Well, in my, well, what I want to have is, it might be empty, yes. But, well, we'll see that it will not be the case for us most of the time. But yes, it could be empty. All right. And I don't think I will need the grand orbit. If I need it, I will define it later. And so, well, these sets are, and the closures are, well, and of course in here, I can write this one as the union as k is positive of fk of x, all right? So that's what I had written before. And so, well, these are the basic objects. And what we need to have, and now I'm going to add some hypotheses on X, is, so if we want to speak about omega limits, well, it's better to do it in the compact case, because otherwise you don't know where you're going, all right? Even if you will see, I will also speak about going to infinity, and that will be part of being stable, okay, having a limit. So when X is compact, we can consider the, oh, sorry, the omega limit set. Oof, French is coming out. Omega of X. And so, well, this is going to be exactly as the omega limit set that Sergei was defining, except that in here, I'm taking the accumulation set of this discrete iteration. Okay? If you want to make a parallel between the two courses of this morning for the moment, E was taking the flow, so at real times, and I'm going to, if I add a vector field, I'm taking the time one flow and I'm iterated at integer times, positive integers. Okay? So, but it's not always going to be the same. But for the moment, if you want to have something in mind and if you're more comfortable with that, please do that. So in here, the omega limit set is the set of accumulation points, meaning that it's going to be the intersection as k is positive of the closure of the forward orbit of fk of x. All right, and the omega limit set is compact, invariant, and invariant. And in here, I had at least to add if f is continuous. But in our case, it's going to be holomorphic. So in here, I'm going to go now to holomorphic dynamics. So you could have, you could ask for your X to be a topological space and having a continuous endomorphism of your space. For us, as I said, we're going to do complex dynamics, and for the sake of being as understandable as we can, today, X is going to be two things. Today, X is going to be either C, okay, the complex plane, or C hat, which is CP1. Okay, so you can see, so this is the Riemann sphere. So I'm taking the compactification. So this is, you can see it as C union infinity. So I'm taking a one-point compactification of the complex plane, and I'm adding a complex structure. Are we good? Do I have to? But I sometimes will want to look at it as the projective plane. Okay, the projective space of dimension 1. Okay, sometimes, I mean, these are the equivalents. So, well, I should put an equivalence because they are not exactly the same objects. They are not defined in the same way, but they are biholomorphic. Okay, are we good? Okay. So well, and for us,
The sphere S2? Yes.
sorry?
The sphere S2.
Yes, it's the sphere S2, but with a complex structure, okay, and a spherical metric, which is giving you holomorphic functions. When I see it at CP1, well, I will give you more details in a second, but the maps that I will consider on CP1 are couples of homogeneous polynomials. Okay, so these are going to be the holomorphic maps that I'm going to take. So essentially, I will try to stay as easy as I can, so either C or C union infinity, but I will keep in mind that I have a complex structure on it. And F is going to be, so will be, is either a polynomial, well, I'm working here, or a rational map. So a rational function, what it is going to be, well, f of z is going to be the quotient of two polynomials of the same degree. Okay, p and q polynomials. So, of course, you can argue that this is simply a particular case of the second case. But what I'm stressing here is that I might consider x without thinking that I'm adding infinity. Or I might add infinity, and in here, these are the holomorphic functions on the Riemann sphere. Okay? I'm not taking all the holomorphic functions on C. I could have also entire transcendental maps, like the exponential, and that goes towards a different path that I don't want to enter in this course, but I could, of course. So in here, what we're going to do, so usually we call this rational dynamics. And this is what we will try to see and generalize in higher dimension, well, if everything goes well. All right? So, of course, yes. Why do I start from dimension 1? Well, first of all, because I have to give you some ideas. And second of all, because this is where the most of the theory is well known. So, from the historical point of view, what's happening is that, well, holomorphic dynamics started more or less with Fatou and Julia. So there was some people working at the beginning of the 20th century, so 1900s, 1910, 1930, and then up to 1940, there was people working on this topic, trying to understand what happens what's the asymptotic behavior and how it behaves when I change the starting point. Because of course you can ask yourself, where am I going when I iterate? But you can also ask yourself, okay, no matter where I'm going, are all the points nearby myself behaving in the same way? Which is a different question, all right? And the two can be related, of course. So, and then there was a stop because of, well, people didn't have the ideas what one could prove, what can you prove and what could be true. And holomorphic dynamics came back to life in the 80s, at the end of the 1980s, where computers arrived. So this is kind of a very good example of experimental mathematics, meaning that this is completely pure mathematics, this is complex analysis at the end of the day, but what's happening is that, well, you get ideas on what you can see by plotting. So at some point, I hope I will show you some pictures so that you can see, and you can see why we're trying to prove some things or some other things, and why this is so difficult when you go to higher dimension, because then you cannot visualize things. I mean, C2, can you visualize C2? Well, that's an issue, all right? Well, if you're very good, I'm not that good, so I cannot visualize C2. So, still, there is a small collection of polynomials where this is going to be easy. I mean, understanding what's happening in here, the asymptotic behavior, and how it depends on the starting point is easy. And so we're going to start from those. And I forgot to tell, I'm sorry, I'm forgetting too many things. But on my side, I arrived very late last night, and I had a very short night. so this is why I'm not at my best today, but tomorrow I will be better. So, all right. So in here, what I was forgetting to say is that I have some lecture notes that I wrote for another class in, well, this was in Cetraro a couple of years ago. And I didn't write new notes for this class, I'm sorry, but you find them already on my webpage. So you go for the, I think it's Fatou components in holomorphic dynamics. I don't remember the title, but it's starting like I'm starting, okay? That's what I'm taking the starting point. And maybe it will be a little different later, but it's going to be, I mean, I'll tell you where to find things and proofs. So as Sergey was saying, I will not be able to give you all the proofs, because otherwise we are not going to ever leave from dimension 1. But I will give you the main steps or some ideas so that you know how to fill the gaps. And that's part of the exercise also. It's like you will have to do some exercise to see where can you prove things, and okay, where do I get stuck, and etc. Okay? But of course, there are also a lot of books in one dimension, like, well, the first one that comes to mind, Milner's book, Holomorphic One-Dimensional Dynamics, so he stays in one dimension. And, well, actually, we have several books in one dimension and almost nothing in higher dimension, but there are some surveys, and I will be happy to point you to those. All right, so we are going to start with, so I'm going to put the first exercise on the board. So that's for later today. So if you take, so let f of z be a linear polynomial, az plus b, and with a and c, well, I would say a and c star, yes, and b and c. Why am I saying a and c star? Because if you put a in equals 0, then there is no dynamics. Then everybody got smashed into a point, and there is nothing left, okay? And then that point stays fixed. So that's not an interesting dynamical system. But whenever you get that this is a real degree 1 polynomial, then what you can do is that you can show that if the modulus of A is different from 1, or if A is equals to 1, but B is non-zero, then the map which associate to Z its omega limit set, which is going to be either in C or towards infinity, could be that we are all going together, this map is constant. So what you have to do to deal with this kind of exercise, first of all, you will have to understand what's the omega limit point, okay? And then just to get ideas on how to prove that it's going to be constant in here. And then in the other case, show that in the other cases, omega z depends on z, and it is either a final set or a Euclidean circle. All right, there is one case which is super easy. I'm going to say it now. Well, if B is 0 and A is 1, that's the identity map. No dynamics relevant to the identity map. The identity map, everything stays where it is. So there is no interesting dynamics. But in that case, it's easy to prove that omega of z is always a finite set, because every point stays where it started. Okay? All right. So, all right. Okay. So I'm going to give you another exercise. So I have 3 exercises, 3 maps, 3 family of maps where you can understand easily what happens to the omega limit set. So that was the easiest case, a linear non-constant map. Then you could also ask what happens for a power map. So consider f of z, which is d to the power d, with d at least 2. And then you can show that the omega limit set of z is 0 if, since it's a set, z belongs to the unit disk. So this is a set of C, so that the modulus of z is strictly less than 1. And omega of z is equal to infinity if z belongs to C minus the closed unit disk. And then you can also show, so in this part, you are seeing that, well, whenever you are in the unit disk, you're going to go towards the origin, which is fixed. Whenever you are outside the closed unit disk, you're going to infinity. Then what's left is what happens in the circle. Well, in the circle, it's not difficult to prove that, first of all, if z belongs to the unit circle, so S1, which is the z in C, so that the modulus of z is 1, then the omega limit set is going to be contained in S1. This is A, B. Okay, omega z can be equal to S1, and C, it can be finite of arbitrary cardinality. What I mean in here is that you can find a point in S1 so that when you consider the omega limit set, it is going to be finite of any cardinality that you would like to have. But it has to be at least one, okay? Any cardinality bigger than 1. I mean, cardinality 0 is not allowed in here, okay? Fine. All right, and the third exercise, so there is another one where the dynamics is kind of easy to understand, is you take f of z, which is z squared minus 2, and then, well, you can prove that for, well, every z in C, I'm sorry, I think I should change this, all right, so that we can see better, can be written, of course, as z equals, oops, sorry, oh, I got caught in my notes, w plus 1 over w for some w in C, with, we're going to have that the modulus of w is equal to 1 if z belongs to the segment minus 2, 2. And the modulus of w is going to be bigger than 1 if you are outside this real segment. So I'm considering the complex plane in here, and I have this segment minus 2, 2. And if I'm here, w is going to be of modulus 1, and outside it's going to be of modulus bigger than 1. And then what's going to happen is that you can also prove that, sorry, B, the omega limit set is going to stay in the segment if you started from a point in the segment. Okay? And so, well, this kind of, well, for the moment, you take them, so you will try to prove them. And actually, of course, you can find them already done in any book. So, but I really advise to try and do these exercises. So these are really special. So in these examples, we can do all the computations. We can, so in particular in this case, there is a first example of kind of changing coordinates to put yourself to a place where the dynamics is easier to understand. But usually when I give you a polynomial, this is not a power map. Okay? And we will talk about changing coordinates. But you cannot change coordinate as you would like to. For example, when you are changing coordinates, since you want to do it for a global map, because you want to understand the behavior on all of C, you have to use isomorphisms of your complex manifold. Well, as a matter of fact, in C, the only isomorphisms that you have are affine maps, these guys. And when you are working on C hat, meaning the Riemann sphere, the only biholomorphisms of the Riemann sphere to itself are Möbius transformation. So these are not going to allow you to change coordinates as you want in all of your manifold. Of course, you can always do it locally. But then if you do a local change, meaning you change coordinates, you conjugate your map in a small neighborhood of particular point, this is not going to give you information on all of the system. Okay? And so, well, actually, I will try to go back and forth from local to global, because especially in the past 10 years, there has been a lot of interaction in between. If I know something on the local dynamics near some point, maybe I can infer something on the global dynamics. That's something that I will try to do. But for the moment, we're staying in dimension 1. I still have half an hour, so I'm doing good. We're going to see already what can we do and what can we say, what are the right definition to use in working in this setting. So I'm saying the right definition because in here, what I was saying was like, okay, let me consider the omega limit set and so on and so forth. Okay, I'm taking all possible limits. But I would also like maybe to understand how the dynamics depends on the initial point. Because in here, yes, in this example, what happens is that, well, what happens for 0? 0 is sent to itself by z to the power d, right? And so, well, if I know that all points nearby 0 are going to behave like 0, then the omega limit set is going to be the same, okay? And, well, same for this infinity. So if I'm in the neighborhood of infinity, I'm going to have the same thing. And then, well, where the chaos is going to happen, it is going to happen in here. As you see, on the unit circle, you can have a mess. I'm sorry to say it like this, but this is what's happening. You are going to stay in the circle, and if you have a neighborhood, sorry, I'm going to do it with a picture. In here, so this is the unit disk, okay? So all points inside are going towards 0. All points outside are going towards infinity. But what happens if I take a point in the boundary? If I'm taking a point in the circle, if I take any small neighborhood, well, every small neighborhood will have points which are outside the closed unit disk. And so we're going to go towards infinity. And points, we're going to go towards 0, which means that you see a transition in the behavior, right? You see a discontinuity. So the right definitions to use in here are due to Fatou and Julia. So we're going to split the manifolds that we had in two parts. A part where the dynamics should be easy to understand. We will see that it's not so easy, but still, it's going to be easier to understand. And the Julia set, where the dynamics is not going to be easy to understand, it's going to be chaotic. And for us, well, our main interest will be the Fatou set, which is already a mess, if I can say it. And we'll see how it goes, okay? Can I erase? Maybe I'm not erasing this. I'm going to stay here. So the Fatou set and the Julia set. So in here, as I said, so morally, but this is not a definition, the Fatou set is the tame set. It is where the dynamics, where we have, well, the omega limit set varies continuously with respect to the starting point. Sorry. I will do it. And the Julia set, well, this is not morally. This is always the case. The Julia set is the complement, so this is the definition of the Fatou set. All right, so once we have these definitions, well, we have to, so we are mathematicians, we're not physicists. Is there anybody in physics in the room? Can I, or we're not chemists. There is no chemist in here, right? There is no chemist in here. I can be, surely I can say this. We're mathematicians, we have to be precise. And moreover, we are complex analysts. And so, well, we have to explain what we mean by varying continuously. I mean, of course, you can try to put some topology on your sets and so on and so forth. But remember, we studied with the family of iterates. So we would like to use something related to convergence. And the right notion to use is normality. Okay, so the real definition is the following. So I'm pretty sure you all know it, but let me write it again. So normal family. So family of map f, say I from U to, I'm going to stay in C hat because this is where it's easier to define things. I have a family, so I have a set of indices. It doesn't have to be the natural numbers, but it can of, so family of holomorphic maps on an open set U, and C hat is normal if for every sequence in this family I can extract a converging subsequence. And when converging, I mean the local uniform convergence of compact sets. Okay? So that's the definition that I will use. Okay, so if for every sequence, so I'm going to call my family F. Everything is going to be called F for capital F or beautiful F, whatever. So for every sequence Fin, where I put in here n now in, well, bigger than 0, so I have In now is a sequence, we can extract a converging subsequence uniformly. So converging, put this in front. A subsequence converges uniformly on compact subsets of U. All right. And actually, so we will see, so note this definition well, because this is going to be the same definition in higher dimension. Okay? Well, you can always define normality. The only thing that is going to happen that we are going to miss and lose and miss a lot Montel theorem. So Montel theorem in dimension 1 tells you that a family of holomorphic maps like before, so this family from an open set, whatever, landing in C hat, which omits at least 3 values, in C hat is normal. So for example, if you take a holomorphic map, which is a polynomial, where it is bounded somewhere, if it is bounded somewhere, for example, take z to the power d, take z squared, if you like. Z squared is going to leave the unit disk, well, it's going to send it properly inside itself. And so while it's going to be bounded, if you take all the iterates, are going to be bounded, that's easy. And if you're bounded, then you're omitting a lot of values, and then you're going to be normal. Okay? Same if you're outside the closed unit disk, you're going to go towards infinity, so the outside of the closed unit disk, it's going to go to a bigger, well, smaller neighborhood of infinity as you like. And so, again, you are going to miss a lot of points. And if you omit 3 values, you are normal. Okay? All right. So, yes.
These 3 points, it should be common for all members in the family, or like
Yes.
all members in the
Yes. All of them are omitting 3 points.
the omitting point should be common.
Yes. Yeah. So, in here, so I said this. Now we can give the real definition, I mean the complex definition of the Fatou set. So the Fatou set of F, so given F, yes, the Fatou set of F from C hat to itself rational is the largest open set in C hat where the family of iterates is normal. And again, the Julia set, so I'm going to give it a name. I'm going to call it capital F of little f. And the Julia set, J of little f, is simply going to be C hat minus the Fatou set. It's always the complement. So just to give you an idea in here, yes. So we're going to see, I'm sorry, I'm being slower than I thought, but is it okay? Are you following me? Do you want me to go faster? Okay. I will not go slower because otherwise I'm going to stay in dimension 1 for forever. All right, so in here, if I want to give you an example, well, let's go towards z squared. Okay, let's do it easily, and then I will leave you an exercise on what happens later. So for z squared, the Fatou set is going to be, so I'm considering z squared on C hat. So it's sending every point in C to its squared, and infinity is going to be sent to infinity. Okay, so it's easy. It's always going to be the case for a polynomial. Okay, a polynomial in C is going to send infinity to itself, a polynomial of a degree at least 1. Okay? All right, so in here, well, if you look at what we saw in here, then you can convince yourself that what's going to happen is that you're going to have the unit disk union the complement of the closed unit disk. And then, well, or if I see it on C hat, I have to put a net in here. And what's going to stay is that the Julia set, I have to take C hat and remove the Fatou set, while all that's left is simply the unit circle. Okay? But this is not yet a proof. I mean, in here we were using limits or punctual limits. So to prove this, and actually this is going as an exercise. Well, the same is true for f of z equals to z to the power d, where d is bigger than 2 or d is less than or equal than minus 2. Okay, so what I'm saying is that this is the same is true if I'm considering z to the power d or 1 over z to the power d. Okay? And, okay. Yes. Well, essentially, I gave you the proof, but I'm going to write it down. I still have 15 minutes, right? 11 minutes? Oh, I'm sorry. Yes, 11 minutes. It's fine. It's fine. It's going to be, yeah, you're right. You're right. Totally right. So, well, let me do it here. Do you see it where I write in here? Okay. So, in here, how do we prove this? Well, the proof, as I said, fk from d to itself. So it's going to be sending d to itself. So let me write it differently. For every k positive, the image of the unit disk is strictly contained in the unit disk. And so f to the power k, f iterated k times restricted to the disk omits 3 values. More than 3 values. Therefore, by Montel, the unit disk is contained in the Fatou set of F. Same for F iterated k times restricted to the complement of the closed unit disk. So what's left is to prove that when I'm on the unit circle, this is not going to work out well. Okay? And so, well, yes. Okay. Again, in here, what this is telling you is that whenever I'm on the Julia set is going to be contained in the unit circle. And now what you really need to prove is that it is equal to the unit circle. By the way, there is something that I forgot to say, but of course you noticed, if this is the largest open set, I'm taking a complement out of an open set, this is always closed. Okay? So now what I want to prove is that there is no point in S1 where I have normality, that I have to add back to the Fatou set. And, okay, yes. And now, well, to use that, it's easy because I'm going to do what I was saying. So note that by the exercise, for every z naught in the unit disk, the omega limit point actually fk of z naught converges as k goes to infinity to 0. And for every, we'll say, w naught in the complement of the closed unit disk, fk of w naught is going to converge to infinity as k2 goes to infinity. Which means that for every z in the unit disk, in the unit circle, sorry, given, how to say it? Yes, any neighborhood of z will contain points in the disk and points in its complement. Which means that you cannot have normality, because when you have normality, then you have either you go to 0 or you go to infinity, right? Which means that actually the unit circle, it is equal to the Julia set. And you can try and do, I mean, it's not difficult, but as an exercise, you should try to prove that the same is true for this power map here. So in the time that I have left, so let me see where I want to go. Well, I'm going to give you the proposition without proof. So why are these sets so important? Well, these sets are important because now that we have split the dynamics into 2 parts, we would like to see and to know what happens on these 2 parts. And we will start by trying and study the Fatou set. Before I go on, let me give you one more definition. A Fatou component is a connected component of the Fatou set. As we saw in this baby example, z to the power 2, we can have two connected components. We can have several connected components, because nobody tells you that the Fatou set needs to be connected. What you can prove is the following, so proposition. The Julia set and the Fatou set are completely invariant. So the image of the Julia set, it's equal to the preimage of the Julia set by F, which is equal to the Julia set. And the same is true for the Fatou set. All right. And, well, maybe I will give a word tomorrow on this. And this is the first property. And the second property, of course, all these properties, I could state them only for the Fatou set. And they are going to be true for the complement, because it's a complement. You just use set theory, which means that to prove all these things that I'm going to put on the board, you only need to do it for the Fatou set, which is kind of a little easier to deal with. Okay? So, yep. So the other thing that is important is that when I iterate my map, the Julia set is going to be the same. So, and the Fatou set as well, for any k positive. All right. And yes, I think, all right. So I think that, well, I will go back to this conjugacy things tomorrow. Is it a problem if I stay 2 hours on one-dimensional dynamics? Yeah, of this course? I know that you pay me for giving a course in holomorphic dynamics in higher dimension, but I really need this stuff. So,
no worries, of course.
okay, is it okay? Because I'm going to need a little more time on dimension 1 before going to higher dimension. So I'm going to simply tell you where we are going to go. So yes. So what we're going to do tomorrow is we're going to see what is the classification of Fatou components in dimension 1 for rational maps on the Riemann sphere. And well, actually this is very well established, so where do I put it? I put it here. So this is now a theorem, but of course it started as a conjecture. So actually there are 2 theorems that are important for us. The first theorem that we will, well, justify, maybe not prove entirely, but we will study tomorrow, is what I call it, I give it to Fatou, because he is the guy who wrote the conjecture, and he proved half of it, but then you should add a lot of people, like a lot of people. I will put only dots. And it's several people finished this proof. But the statement is easy, so let F be a rational map of, function of degree d at least 2, because otherwise we have seen it's not interesting. And, well, an invariant Fatou component, omega. Invariant means that f of omega is going to be equal to omega. Okay, so a Fatou component which is instanted to itself, and we will understand tomorrow why this is so interesting, is, well, it cannot be whatever. Either an attracting basin, or a parabolic basin, or a rotation domain. And I will give you precise definition tomorrow, but for the moment, let me give you the idea on what we have in here. So an attracting basin is simply going to be, well, it's open, it's connected. Actually, it's simply connected. There will be a fixed point somewhere, and every point, every orbit will converge to this attracting fixed point. It could be a parabolic basin. So a parabolic basin is somehow, you can see it as a different degeneration of this picture when you send the fixed point towards the boundary. So the fixed point is not going to be in the Fatou set anymore. It's going to be in the Julia set. But I will have a fixed point in here, and all these orbits are going to converge there in a given way. It's not, I mean, they're not going to be like this. They're going, when they are nearby the boundary, they're going to do something like that. And we will spend some time on this part. But it could also be a rotation domain. And when you are in rational dynamics, rotational domains can be either biholomorphic to a disk, so you have a fixed point inside, and all the other orbits are rotating around it. Or it could be, so this is simply connected, or it could be doubly connected. It could have a hole inside, and this is an Hermann rim. And so there is no fixed point, but every orbit is rotating, okay, in this annuli. And why is this close in the picture? I'm going to steal you 1 minute, and that will be it. Well, this is close in the picture because there is a theorem of Sullivan that I will not prove, Sullivan, in 1985, which tells you that if f is rational from the Riemann sphere to itself of degree at least 2, then every Fatou component is pre-periodic. What do I mean by this? Well, I will give you the definition tomorrow, but what you have to keep in mind is that your Fatou component can wander around a little bit, but at some point it will have to enter in a cycle. So if you think about it, we will see tomorrow that actually considering the Fatou set gives us a new dynamical system because we can see the action. We can ask what happens to the action of f to Fatou components. The image of a Fatou component is always going to be a Fatou component. So it could be invariant or it could be wandering, but this theorem tells you that it cannot be wandering on the Riemann sphere. So in here, we have to have a finite orbit. Okay, so it's a finiteness orbit condition that we're going to have in here. And of course, what do I mean by this ends the picture in dimension 1? I mean, it doesn't end research in dimension 1, but if you want to understand what happens to Fatou components, this is all you need to know. Because if you take now any Fatou component in here, well, up to a nitrate, this is going to stay invariant. You know, it's going to end up where somewhere it is invariant, and then, well, you will know what the dynamics is going to be, and also you will know the geometry of this, because you have Riemann's uniformization theorem. Okay, so this is where we are going tomorrow. So tomorrow we will spend a little more time on this theorem. I will not prove this one, but I will give you an idea, well, where you can find it. And I think that's it for today. I'm sorry, I stole you 2 minutes. Actually, I was supposed to talk 55 minutes, but you didn't complain too much, so it's okay. If you have any questions.